good morning, or good afternoon. Maybe you're watching this in the afternoon. Either way, good day to you. Today we're going to be talking about solids. We are starting our next unit. We're going to be talking about surface area and volume. Today we're just going to define a whole bunch of stuff, and then we'll get into more specific shapes later in the unit. So let's go ahead and get started. Oh, one thing, I did post a schedule for the rest of the year. So the next 2 weeks, we're going to be doing solids. The very last week, we have 2 days. Our last day is going to be goodbyes and maybe one last math problem together, because why not? And the day before that, there is a skills assessment where I will be giving you a 25-question multiple choice test. I know I said I wasn't going to be giving you any tests, so this is not graded, but the math department would like you all to go into the summer knowing what skills from this class you have mastered and which skills maybe you could refresh your memory on. I am also going to be giving you an optional Algebra 1 skills assessment because you are going into algebra next year. So if you would like to refresh some algebra, that can help you determine what kinds of things to spend your time on during the summer to help prepare for next year. So that's coming. Once again, it's not graded. You will get a grade for completing it, and I do want you to take it seriously. Okay, moving on. So today, exploring solids. So a polyhedron. A polyhedron is a solid where all the sides are polygons. Okay, solid with polygon sides. The faces are the polygons. Okay, those are the sides. The edges are the segments where the polygons meet. And the vertex is going to be where the edges meet. And that's going to be a point. Okay, so over here we have a picture, and it's hard to see, but this right here is the edge that's highlighted. So a face is just a polygon, a vertex is a point on the corner, and an edge is the side where two sides meet. Is the segment where two sides meet. Yep. Okay. So here are some examples of polyhedra. So the word polyhedra is plural for polyhedron, and some not polyhedra. So prism and pyramid are 2 examples of polyhedra, and we're going to define each of those in a minute. And then a cylinder, cone, and sphere, those are all solids, and we're going to be talking about them in later sections, but those are not polyhedrons. So a prism. A prism is a polyhedron that has 2 congruent and parallel bases. Okay, so 2 congruent and parallel bases. So if I look at this top one, here is a rectangle on the bottom, and that's congruent to the rectangle on the top. They are parallel and congruent. A pyramid is where I have a polygon base, so 1 polygon base, so maybe I should say that, 1 polygon base, and triangle sides that meet at a vertex. Okay, so I have 1 polygon on the bottom, so here I have a quadrilateral on the bottom, and then I have 4 triangles that meet at a top vertex. Down here I have a triangular pyramid because I have 1 triangle on the bottom, so there's my base, and then all the other triangles meet at the top vertex. So another example of a prism, going back to that, is here is a pentagon base, and it's congruent to another pentagon that it's parallel to, and all the other sides are going to be polygons that connect the 2 bases. So that is a prism. All right, examples. So for these 3, determine whether each solid is a polyhedron. If it is, name the polyhedron and find the number of faces, vertices, and edges. So go ahead and pause the video right now, try these 3 on your own, and then come back and check. Okay, so the first one, we have a basic block almost. So is it a polyhedron? Yes. Why? Because all of the sides are polygons. So polyhedron, yes. Okay. Number of faces is going to be the number of sides. So I have the front, the back, top, bottom, left side, right side. So there are 6 faces. The number of vertices are going to be the corners where those faces meet. So I have 4 corners in the back and 4 corners in the front. So there are going to be 8 vertices. And then the number of edges are going to be the number of segments. So on the back, I see that I have 4 segments to create that back rectangle, 4 segments to create the front rectangle, and then 4 segments to connect them. So I have a total of 12 edges. Okay, so my next shape looks like a pyramid. So let's see here. Let's double check. Yep, I have a hexagon as my base, and then all of the sides are triangles that meet at a vertex. So yes, that is a polyhedron because all of those are polygons. The number of faces, so let's see, there's 6 triangles, and then there's 1 base, so there's going to be 7 faces. The number of vertices is also going to be 7 because I have 6 vertices on the bottom. Okay, so those vertices down here, and then 1 vertice at the top. So I have 7 vertices. And then I'm going to have how many edges? So let's see here. There are going to be 6 edges down here. 1, 2, 3, 4, 5, 6. And then 1, 2, 3, 4, 5, 6 edges there. So then my edges are going to be 12 edges. And then my last one, is it a polyhedron? No. Okay, why? Because a circle here is not a polygon, so not a polyhedron. All right, theorem time. So this is called Euler's theorem. I know his name is spelled Euler, but it's pronounced Euler. Oh my gosh. This theorem should be in one line. So let's pretend there's an enter there. So your theorem is F plus V equals E plus 2. So the theorem says the number of faces F, vertices V, and edges E of a polyhedron are related by the formula F plus V equals E plus 2. And they give us an example of a cube here. So there are 6 faces, 8 vertices, and 12 edges. So 6 plus 8 is 14, which is the same as 12 plus 2. And if we look up above, that's the same for our first example. Our second example, 7 plus 7 equals 14, which is the same as 12 plus 2. So fantastic. So it works for our 2 examples. So we are not going to prove this theorem. We're just going to believe Euler because he's, some old genius mathematician. So usually they're right. Standed the test of time. So for our next example, find the number of edges on the frame of the house. Well, this looks more like a shed, but it's a basic house. Cool. All right, so it's kind of hard to see because I got a shadow going on here. So if I look at this, I have a front, a back, and then they are connected here, 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 and here. Okay, so find the number of edges on the frame of the house. Okay, so let's use the theorem. So faces plus vertices equals edges plus 2. Okay, so how many faces do I have? I have front, back, so front, back, side, side, so 4, 5 for the bottom, and then 2 to make the roof. So there are 7 faces. And then the number of vertices is going to be 1, 2, maybe I should use in a different color. Vertices, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 vertices is going to equal E plus 2. So then there are going to be 17 is the same as E plus 2. So I better have 15 edges. All right. It's better than counting them all. Okay, now we're going to define a regular polyhedra, and then we're going to talk about convex versus concave. So a regular polyhedra is where all of the faces are congruent. Oh my gosh, my pen is running out. Okay, so all of the faces are congruent for a regular polyhedra. And then we talk about convex versus concave. So remember, concave is where if I connect any of the vertices of a polygon and that goes outside of the polygon, then it's concave. Okay, so that's the same thing for our polyhedra. So if there's any kind of indentation, then we say it's concave, where if it creates a concave at all. Okay, so you can see here is an example of a concave in that picture. Because I have a line that I can connect to the vertices, and that line is outside of my figure. Okay, so Platonic solids. So Plato, is a Greek philosopher back in 427 through 347 BC. And he really talked about these 5 solids. And so they're called the 5 Platonic solids. And so we have our regular tetrahedron, we have a cube, we have a regular octahedron, and we have a regular dodecahedron, and a regular, I don't even know how to pronounce that. So basically here are some regular things. So 4, 6, 8, 12, and 20 sides were the ones he really thought were special and worked a lot with. Okay, so there are many other ones, but just so you know, these were used by Plato. A lot. All right. Examples. All right, so here we go. So here is a regular octahedron, and use Euler's formula to find the number of faces, vertices, and edges. All right, go ahead, pause the video, try it on your own, and come back and check your answer. Okay, so if we look at this by counting, we see that we have 8 faces. Okay, so 1, 2, 3, 4, and then 1, 2, 3, 4 on the bottom. Okay, so 4, so 8 faces. And then if we wanted to count the vertices, we have 1 and then 4 in the middle and then another one at the bottom. So our vertices is going to equal 6. And so then if I wanted to find the number of edges, I would say, all right, my formula tells me faces plus vertices equal edges plus 2. So 8 plus 6 equals E plus 2, so 14 equals edges plus 2, so my edges is going to be 12. Okay, and then let's count our edges. Let's make sure 1, 2, 3, 4, and then 1, 2, 3, 4, and then there's 4 in the middle. Yep, so edges equals 12. Check. Okay, next and last definition is a cross section. So basically, a cross section is when you slice your solid. Okay, you're just taking a slice of it, kind of like a slice of bread. All right, so if you're just slicing it with a plane, what shape does your solid make depending on how you slice it? Okay, so the intersection of the plane and your solid is called the cross section. Okay, so the cross section is the intersection of the solid with a plane. Okay, so think slice. All right, and the cross section is just that shape right here where they intersect. Okay, so describe the shape of the cross section. So if I have a cube and I do a cross section that's parallel to the bases, I'm going to have probably a square or a rectangle, depending on if that's a square. Ooh, B, it's kind of interesting because I am going diagonally. So we've had some of these before where we talked about what that would look like. And so now if I'm going diagonally from edge to edge through my cube, that is also going to be a rectangle. Okay, it's rectangular shape. And then C is really interesting because if I look at C, I'm going at a corner, but I'm not going from edge to edge, and I'm not going from vertice to vertice. So I'm just kind of peeling off part of a corner. And the way that one's oriented, that looks like a trapezoid. Okay, so C is a trapezoid. All right, and my pen died, of course, so I can't write that down, but you can. All right, so that is your introduction to solids. Go ahead and turn in your notes and start the homework. Thank you. Oh, now it works.